right. Advent of Code 2020 day 14, the halfway through edition. So by the time we're done Advent of Code today, we'll be halfway through the entire thing, which is pretty cool. It's a pretty big milestone. Advent of Code is definitely one of those things that it's easy to start and then easy to fall off. And I certainly haven't fallen off yet, but it's the month is far from over, but halfway is a good place to get to. So I'm happy about that. So yeah, let's get started on day 14. Advent Code, where are we? This guy. All right, we're still here. Return to your Advent calendar. Day 14. Docking data. All right, let's just copy this into the old paste buffer. Okay, as your ferry approaches the seaport, Captain asks for your help again. Computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bit mask in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. Okay, that's cool. The initialization program, your puzzle input, can either update the bit mask or write a value to memory. Okay, can either update the bit mask or write a value to memory. Values and memory addresses are both 36 unsigned integers. 36-bit unsigned integers. For example, ignoring bit masks for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. Okay. The bit mask is always given as a string of 36 bits, written with the most significant bit representing 2 to the 35 on the left. Okay. And the least significant bit, the ones bit, okay. The current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. Okay, so this is like an overwriting mask. So if we leave it as an X, then it leaves it whatever. Okay. For example, considering the following program: mask memory 8 equals 11, memory 7 equals 101, memory 8 equals 0. The program starts by specifying the bit mask. The mask it specifies will overwrite 2 bits in every written value. The 2's bit is overridden by 0, and the 64's bit is overridden by 1. The program then attempts to write the value 11. So that's the program. So they give us this mask. Oh, excuse me. Sorry, I'm yawning. They give us this mask, and then they give us these memory things. Okay. Then attempts to write the value 11 to memory address 8 by expanding everything out into individual bits. The mask is applied as follows. Okay, so decimal 11. And then the mask is that. Okay, so then we end up. Interesting. So the mask overrides what we're putting in. Okay, so because of the mask, the value 73 is written to memory address 8 instead. Then when the program tries to write 101 to address 7, the value is now decimal 101, and then this is the same bit mask, so the bit mask remains unchanged, and then the result is this decimal 101. So this time the mask has no effect because, yeah, okay, it doesn't line up. All right. Finally, the program tries to write 0 to address 8. And that basically just, okay, 64 is written to address 8 instead. So it tries to write all zeros and 64, which is, I think, the value of the bit mask right now is 64, yeah. To initialize your Fairies docking program, you need to sum all of the values left in memory after the initialization program completes. The entire 36-bit address space begins initialized to the value 0 at every address. In the above example, only 2 values in memory are not 0, 101 at address 7 and 64 at address 8, producing a sum of 165. Execute the initialization program. What is the sum of all the values left in the memory after completes? Okay, so like, I think I'm kind of getting an idea of what it is that they're asking. So basically, they give us this starting mask, then we need to make masks for these. I don't understand yet what this memory address 8, memory address 7, memory address 8, like, does that change something about how we apply these? This time the mask has no effect. Okay. Tries to write it to memory address 8. So producing a sum of 165. I mean, maybe we'll understand it as we try to implement it. That's a terrible way. Terrible way to program, but you know what, sometimes it's what you need to do. Sometimes you need to sort of like start wading into the problem, and then you're just like, oh, this is why that's important, or this is what this means. So let's give that a shot. Let's just make a program. Okay, so bitmask, consider the following program. So we've got this program. So I think this program is our input. Let's go with that. All right, this program starts by specifying a bit mask. Okay, so we got some plain and whoops, plain, and then plain. All right, cool. So what we're gonna want to do is we're going to want to make sure that the sum of all of these memory locations, memory 8, memory 7, memory 8. So this is weird, but this memory 8 override this memory 8? I think it does, because then we get decimal 73, decimal 101, 64, and then we're just adding 101 and 64 to produce, yeah, it's adding, right? The only 2 values in memory are not 0, 101, 64, producing a sum of 165. Okay, so I think I understand this. Like, each one of these memory locations, like, we're gonna sum the entire memory array and produce the output. So okay, let's see if that's correct. So we've got our definitions, we've got our tests, and then we're gonna have the bit where we run it. Still have yet to come up with good names for these sections. We'll bring in our usual compatriots. So we're gonna bring in log and assert. Cool. And we are going to be asserting, so finally we're gonna be asserting that 165. We're gonna assert that 165 is the sum of, or is the register sum. It's going to be the sum of arrays, all those array values, right? So we'll just write some English here. Sum of what do they call them? Memory addresses. Sum of addresses. Okay. And we're gonna have some more stuff. So first and foremost, we're gonna need to parse the input. So that's always, we always take in a block of text. Oops, doesn't need to be fat arrow. Okay, so it always takes in a block of text. This is what the input looks like. So I'm just going to copy this down here so we can look at it as we're writing this method. Cool. So we're gonna have a mask. So this bit mask here. So this bit mask is going to serve two purposes. One, it's going to tell us which bits of these numbers are going to be allowed through, or going to be blocked, I guess. So the X's are going to be applied, and then the non-X's are going to be sort of like written over top. Now this sort of reeks of binary arithmetic, and every time I see binary arithmetic, I always have to like remember like which one is which again. Is it's like, because there's X and, so like what's X and is when it's like 1 and 1. X, what was this? Xander, okay. XOR, all that stuff. Let's see if we can find a table. I think there's a picture of a table here. Where we go? No. NAND. Anyway, we'll come back to that in a second. So we've got the mask, then we've got these addresses. So effectively what we're going to be doing is we're going to be turning these into binary strings. I guess we're going to turn them into binary numbers, and I think what we're going to do is we're going to be ANDing those with our bit mask, and then we're going to be applying the value of the bit mask. Or I guess we're going to be ANDing it with the value of the bit mask. Is that what it is? No. Specifying a bit mask. The mask it specifies will overwrite 2 bits in every written value. So yeah. So is that AND, or is that, or is it, no, I don't know. NAND? I forget. Let's look. Binary arithmetic. Come on, just find me a good simple table. That's binary shifts. We don't care about that. This is multiplication, subtraction, addition, chart. Sure, give me a chart. I don't know. None of these seem to be what I'm looking for. I don't know. We'll just look it up in a minute on like one of the JavaScript sites, and just be like, look up XOR and XAND and stuff, because I feel like these are going to be one of those. So here we have the value that we're putting in, and then there's this mask. So the mask, as I see it, is here. I'm going to copy this so I don't screw this up. So the mask is going to serve two purposes. The mask, we're going to basically have all of these X's, or I guess all of the non, and then all of the X's are going to be false. That's my idea of the mask, is we're going to convert it to it as bit mask. So this is going to be our mask, and then this is going to be our mask value. Or no, this is the mask. So this is going to be the mask itself. And then this is going to be the mask value. So what we're going to want to do is we're going to be in the, was it the initial value? And we're going to want to, like, I think, AND it with that. And then we're going to like OR it with the mask. We're gonna have to figure this out. So this is like my thinking is like it's gonna be a couple of binary operations. Yeah, okay, so parse input. For now, let's focus on pulling these memory things out of parse input right now, just so we can start on something. I guess we need to parse all these things. So yeah, okay. So we're gonna say, let's do this in 2 steps. We're gonna say mask equal text. We want to match globally. We want to match for mask equals. So equals, and then we're gonna have x 0 or 1, capital X. Oops. So we're gonna have the word mask, and then we're gonna have x 0 or 1 a certain number of times. Okay, I'll deal with that in a bit. Turn that on. There you go. I'll just see what he wanted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So 36. There's going to be 36 of these. 36 is going to be global. So let's see what this does. Match. Let's just input. This is saying match is not a function. No, it's the input. It's the other way around. Input dot match. Okay, so that gives us this because it's global. Okay, there we go. So this is going to give us. So the first result is the capture group. Okay, so so parse input. There we go. So this is going to be text. So it's going to be something to throw away, and then the mask is going to equal that. And now we're going to want to do the memory ones. So let's figure out the memory ones. So it's going to be similar, where it's like mem, and then we're going to have. Did it say how many memory addresses? Did I just like miss that? Let's take a look. Are both 36. Values and memory addresses are both 36-bit unsigned integers. Okay, so it could be a very large number of memory addresses. Okay, so this is going to be a multi-digit thing. This we have to escape because it's a square bracket. And then we're going to have, these are going to be digits, and we're just going to say plus. Okay, so this is going to be how we match memory addresses. So let's take a look at these. What do we got? We got 8 and 11. So that's 8 equals 11. And do we want to? I think we're gonna have to exec these. So because this is just gonna give me the first match. I know if we do global, whoops. Yeah, if we do global, it gives us just the matches back. So we don't actually want that. I think God damn it, I keep doing that. Okay, so if we do non-global, I think what we can do is we can do exec. We can exec these against input. And I think we can do this iteratively. So we can say while address value equals that, then we'll like log add value, and then we'll log done. Let's see if this works. Nope, it doesn't. What if we, maybe it's because we're making new regex each time. No. There, stop. So regex exec, let's Google it. While array equals regex exec is not equal to null. Okay, so this is supposedly how that works. So they make a regex object, which we do here. Well, exec against the string is not equal to null. Oh, you know what? Maybe it's well, yeah, result. Let's capture it in result. Equals result, and then we'll log that. See if no, it's still not working. Interesting. So why does this not work? So this is, they were making a regex object and we're execing it. Is it because it's, should it be global? Yeah, it's because it should be global. Okay. Can we collapse this? That's another question. Is this the same? No, it's not. Okay. Okay. So this is what we've got. We're gonna do. All right. So we're gonna grab this, and we're gonna put this in our parse input. So we got our mask, and now what we're gonna do is. So this is going to be mask pattern. Okay, and then this is going to be mem pattern. Cool. And results. Whoops. This is going to be mem pattern. Cool. And instead of logging them, so what we're going to have is we're going to return an object, which is, okay, so we've got mask, and then what we're going to do is we're going to have mems, mems equals array, and say mems at address equals value, val. I guess we can put that there, and then we're going to return mask mems mems. Okay, so let's try this parse input and see what we get back and see if it's awful. Parse input. So we're going to log parse input. It's angry. Add is not defined. Oh, okay, right, because we're not destructuring. Well, I wonder if we can do this. Oh no, we just tried this. Okay, so let's just not do that. Okay, so we need to destructure add val, and then we can do that. No. Add is not defined. Oh yeah, equals result. Okay, so 7 empty items, then 8, and then it's then 7 and then 8. So 7 empty items would be 0. 101 0. That doesn't seem right. 101. And the value is 0, so that is right. 101 and 0. Okay, beautiful. Cool. So we've got our memory items, and we've got our mask. So I guess the other thing we could do now is we could process the mask. I guess we need to figure out how we're going to apply the mask. So one thing we can do is we want to create these decimal values. So decimal 73. So where we have 101, for example, we want to write that as a binary string. So I know that like there's like parseint, but is there like the opposite? JavaScript binary from decimal. I guess it would be decimal to binary. So parse in to string 2. Okay, let's just try that here. Let's log 73.toString2. And we want to 0 pad that, I think, to this, or I guess it doesn't matter if it's 0 padded. Oh, maybe it does though, actually. It does matter that it's 0 padded, and that's why they want us to, right? Is there just an easy, like, is there an easy 0 pad or left pad? I don't want to use left pad. So pad start. Okay, there we go. Pad start. Cool. So pad start 2 0 pads the current string with another string multiple times if needed until the resulting string reaches the given length. Okay, so let's try pad start. So dot pad start, and we're gonna say 36. Is that how it is? Yeah, 36 with 0. Okay, beautiful. So so now we got the number 73 represented as binary with, at least it should have 36 digits. 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 36 digits, and that's how many digits we have here, right? Yeah, 36. Beautiful. Okay, so this gives us the binary representation of that. Now what we're going to want to do is we want to apply these transformations. So all right, let's step through these transformations. We put this off long enough. Okay, so the mask is going to overwrite. I guess what we can do is we could represent these. We could break this into an array, and we could represent each of these as like undefined. And then if it has a value, we could overwrite the value. So the mask value 73 is written to memory. Okay, because we don't care that it's a 0 or a 1 until we go to evaluate it later. Like for the mask, we only care that that it's a 0 or 1, or that it exists, that it's not an X. So let's just write a quick apply mask function. We might be able to get some performance improvements by turning it into a binary number and applying like a bitwise operator to it. But let's just do it the naive way, just to see if it works. So we're going to take the mask in, and we're going to take in a number. So the mask is going to be, let's assume it's a string, like what we get in up here. And then let's take in an int. So an integer, and we'll apply the mask and we'll return an integer. We'll return the result, which is an integer. So the mask here should be 36 bits. And what we care about is we care about just overriding these numbers. So the first thing we're going to do is we're going to want to turn the integer into a string. So int bin string equals int to string, and then we're going to add the start. Okay, and then we're going to have the mask. And so for char in mask, actually, let's get the index of that when char isn't x. So basically, we're gonna go through the mask, and every time the mask isn't an x, what we're gonna do is we're going to just override this at index with char. And then we're going to parse int that as binary, and we're going to return that. So okay, so we convert our integer into a binary string. We pad the start with zeros, and then for every character in the mask, so we're going to go through the mask bit by bit, where when it's not an x, because we don't care about the x's, we only care about the non-x's. What we're going to do is we're going to override the binary bit string at that position with that character. So it's literally just going to be like a photoshopped layer sitting on top of it. And then at the end, what we're going to do is we're going to parse int the bit string, the resulting bit string, after we've modified it as binary, and then return that in. So let's test this. So let's apply mask to, let's just get a mask. Okay, so this is the mask, and the value that we're putting in is going to be 11, and the result should be 73. So we don't need these things anymore. I don't know what I was doing there. All right, apply mask with 11, and let's log that. Oops. Log apply masks, and it is giving us back 11. So that's not what we were looking for. What we were looking for is we're looking for 73. Int bin string. So let's log that, and then let's log it again after we're done. So this is the, why are we logging it 3 times? Where's that log coming from? That is coming from, oh, that's 73. Okay, so we got our log. Okay, so int bin string is coming in mask, oh, split. Let's split on nothing. I guess what we should do is we should treat these as arrays. Okay, so this is becoming, there you go, toString, pad the start, and then split it on nothing. So this is our, we'll just call this bits. We're gonna log bits, and then we're gonna do the same thing for mask. I'm gonna say bits, and then we're gonna log bits again. We'll log these by joining them with nothing, so we can actually see them. And basically we're gonna parse the bits joined with nothing. Okay, so this is what we get back, and now we got 73, good. Cool, we can get rid of these logs. Okay. So we got bits, then we modify bits, and then we parse int the bits, and that gives us our output. So that's good. We can assert is, that's what they wanted, assert that, and then what else do they want? So 101, they want us to assert that 101 is 101 still. 101, 101, that still works. Still logging something up here, which is annoying. Okay. And then what else do we got? Assert 0 is 64. Assert 0 is, or no, 0 is 64. Whoops. There we go. Beautiful. Okay, so now what we want to do is we want to take this input, and we want to produce a new memory array. So this is going to be init program, and this takes in these defs that we get back from parse input. So we're gonna get back mask and mems. So mask is a string, and then mems is an array. And what we want to do is we want to apply these rules, I guess. We want to apply the mask to all the memories for mem in. So I guess we can just mems.map mem. And we can then apply the mask. Apply mask mem. Yeah, that's fine. And then what we're going to do is we're going to sum mems, right? Is that it? And then and we want to sum array mems. And we wrote sum array earlier, so we're just going to steal it from day, what is this, day 9? All right. That way we don't have to write this again. So this is going to be array equals whatever, array reduce memo val equals 0. That way it's got a nice in case the value is null, like in the event that the array has no entry, it'll be null or undefined or something, and this will just default it to 0. So 0 plus 0 is 0. And that's all we care about. So let's assert that init program, and we're going to have input. Oh, it's not input, it's actually going to be parse input. So parse input, that gives us back mask and memes. So I guess what we could do is we could just bring this back as an array. And then here we could just, I guess we could explode that. Yeah. Parse input, input, and we'll explode that. So assert 165, oh yeah, is. So it did not work. So why is that? Let's find out what init program is. Let's log in. Oops. 1010. That's interesting. Let's log mems here and see what we got for mems. So we got 7 empty items, 101, and 0. Oh, so that's interesting. So that's actually. Okay, wait a second. So 101 and 0. So this is giving us a 0 back, even though we applied the mask, and it should have given us 64. Oh, that's because we're not capturing the output of map. That's right, mems. I guess what we can do actually is we can just sum the array here. So it'll sum the output of mems map. And that gives us 133, which is also not what we want to do. So let's say ret equals that, and then log ret and sum array ret. Okay, so what do we got? 7 empty items, 69, 64. So that's not correct either. So what we should be getting is, I think we should be getting, yeah, we should be getting 101, 64. So why is it giving us 69, 64? So applying this mask to 101, which is here, should give us 101. And applying this mask should give us 64, and it does. Or I guess, what is that, 11? No, decimal 0. Because what do we have? We have equals 11, which gets overwritten. 101 and then 0 should turn into 101.64. And what we're getting here is 69.64. So that's very confusing. Why are we getting that? Let's look at it. Let's log mask and mem. So mask is 101, mask is 0, and then we're getting back, oh, that's interesting. And then let's log apply mask. Okay, so that's really interesting. Applying this mask to 101 is giving us 69, which should not be the case, because look, we've asserted down here that it should be 101. Unless it's this, is this the assertion that's failing? That's super confusing. So here we have this assertion. Yeah, let's just line these up. So if we apply, we're calling apply mask, and then the value at this memory location. And we're saying we're logging the mask, which is this, and the value at that memory location. Is that value? Oh, it's a string. That's why. Okay. Parse float. There we go. Okay. Oops. This is mem's mask. Okay. Yeah, and then yeah, we actually can just sum that array. Whoops. There we go. And let's assert that 165 is the thing. We don't need to log it anymore. Okay. Good old parse float. Forgot to parse the float. All right. Cool. So now we're going to run our input. So we're going to need to get the input from here. Okay, your puzzle input. Okay, big masks, big numbers. Should be fine. Yeah, we're gonna have to create an input file. I mean, this is probably not the fastest way we've ever done something, because we're gonna be creating a gigantic array with a lot of empty, a lot of like, it's gonna be an extremely sparse array, because look, we got 37,000, 49,000, and like, you know, we're gonna have just a ton of empty things. Oh, also, that's interesting. Look at this. We're gonna have masks followed by memory assignments, and each time we do this, is that what they said in the thing? Each time we're gonna zero out. Okay, it starts out by specifying a bit mask. We'll overwrite 2 bits in every written value. Left in memory after the initialization. Okay. So it wouldn't zero out the array, but it would change the bit mask, I think. Okay, it uses a strange bit mask system. Your puzzle can either update the bit mask or write a value to memory. Okay, so yeah, what we want to do, I guess, is we just want to iterate over it line by line and apply the rules. So let's update that. So assuming this is what we have in, then what we're going to need to do is we're going to process it one by one like that, and we can just so we can say, okay, we'll just say text dot. So what are we going to do here? We want to process these as either a memory command or a mask change. And we're going to want to know what they are. And I mean, this is basically going to happen in init program, except, yeah, see, the way that the way we've written a init program is now not great, because it's assuming that there's one mask and then a bunch of memories, and then we just apply the masks, and then Yeah, we're gonna have to take a more iterative approach here. So maybe parse input doesn't even necessarily make a lot of sense. So my dog is barking. Split on new lines. I guess what we're gonna want to do is we're gonna want to parse line, and we're gonna want to basically evaluate each line. I mean, we could do this with, like, for the most part, aside from the mask ones, we could do this with like JavaScript eval, which is super gross. I'm not a fan of that, because actually that's not even true, because this wouldn't work. We'd have to put in like our own. We'd have to quote our values. I mean, which we could do. I mean, yeah, but not a fan of that. I'd rather pull them out and assign them specifically, even though that might be more error prone. It's certainly safer. I know we have a fixed amount of input here, so we can actually we can trust the input, because we can inspect the input before we put it in, and we know that this is the only input coming into our system. It's not. I don't feel like it's a good practice though. So let's. Okay, what are we gonna do? We're gonna parse line. And this is going to give us back a command, or I guess like a thing to assign, and then an argument or two arguments. I guess what we can do is we can just say equals, sure, line, and that line's going to equal, it's going to be a text. And we're gonna want to pass in mask the current mask, the current memory in the line, I guess, or this is gonna be process line. I'm gonna take in the current mask and the mem array. Oops. And then the line to process. And then what we're gonna return from that is we're gonna return the mask and the mem. Okay, so if mask pattern test line, what we're going to do here is we're going to apply the mask pattern. We're going to say mask equals line match. We'll do that. Whoops, there we go. Else if mem pattern, then this mem pattern doesn't need to be global anymore. Then what we're going to do is we're going to have add value equals mem pattern, or text. It's not text, it's line. Line. Dot match mem pattern, and then we're going to say mem address equals parse float. Wow. Float. Parse float val. And then we're going to return mask mem. So this is going to be our process line. And then process lines, or I guess process input. And this is going to take text, which is a big ball of text. And we're going to say for line in text split. We're going to, so mask mem equals, we're going to initialize mask and mem. I guess we can do that here. We can say mask equals nothing and mem equals empty array. Sply. Then we can say mask mem equals parse line, process line. Mask mem line 4. Let's put this on another line. There we go. And then we'll return mask and memory. And then what we're going to do is, I guess for a init program, what we're going to do is we're going to take in, so this is going to be its mask and memory. That's going to process the input. Actually, what we could do is we could actually just sum the array here. Mem map. That's going to be a value. So that's going to be process input. So it's not init program, it's going to be process input. So let's see if this works. Process input, input. It does. Okay, well, sure. Let's roll with that then. It's not parse input we don't need anymore because we're not using it. So we've got process input, which calls process line. Process line just basically updates the mask and the memory. And then what we're going to do is we're going to sum the array at the end, which is this guy. And we're using apply mask in sum array. Yeah. Okay, and it's passing our assertions. I'm surprised all that refactoring passed assertions, but let's roll with that. Log process input, and then this is going to be require input. And the number we get is this. So let's see if this is the answer that they're looking for. That's not the right answer. Your answer is too high. Oh, it's a big number. I'm not shocked that the answer is high. Okay, turn to day 14. So let's log. We know it's 165 here. That's a big number. So, oh, here we got a problem. Yeah, so what we're doing here is we're actually applying the mask after the fact, which means that we've already updated the value. So this is going to use the last value of mask. So that worked in our first case where the mask never changed, but it's not going to work in this case. So we're already going through this line by line. So then process line mask mem. So in process line we should apply the mask is what I'm thinking. So parse float val is going to be the number, and then we're going to want to apply the mask. There we go. So maybe we can do that, and then we can just sum the array. Cool, and it still passes our input, and it gives us a different very large number. But this makes sense to me. So we're going to sum the memory array. So we're applying the mask as we know the mask, because we keep passing the mask in each time, because we're updating the mask here. And if it's a mask, we update mask and then pass it back. And then on the next round, what we can do is we pass this mask back in. Okay, so let's get that and see if this is the answer that they're looking for. The word mask is not what I meant. All right, submit. That's the right answer. Okay, cool. So how far into the stream are we? Like an hour? Yeah. Almost an hour. It took us an hour to do part one. It's okay. It's not a race. I guess it is a race for some people. It's not a race for me. New file. Input or 2.lit coffee. Cool. So here we are with part two. And I'm just going to do this now. The following program. This is gonna be our input. Okay, then we got these. I don't know what this means yet because we haven't read it. That's okay. I'm just doing a little markdown gardening. Whoops. There we go. I feel like it's a good opportunity for my brain to sort of like reset after thinking about that stuff. Defs, tests, run. Okay, cool. There we go. All right, let's read this bad boy. Part two. For some reason, the C ports computer system still can't communicate with your Fairies docking program. It must be using version 2 of the decoder. Okay, version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. I don't know what that means, but there's a link. Okay, immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If the bit mask is 0, the corresponding memory address bit is unchanged. If the bit mask is 1, the corresponding memory address is overwritten with 1, and if the bit is X, the corresponding memory bit is floating. A floating bit. Okay, I'm glad they're defining what a floating bit is. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. Well, come on, guys. Okay. For example, considering the following program. With this program, goes to write to memory address 42. It first applies the bit mask. Okay, after applying the mask, 4 bits are overwritten, 3 of which are different and 2 of which are floating. Floating bits take on every possible combination of values. With 2 floating bits, 4 memory addresses are written. Next, the program is about to write to memory address 26. But as 3 floating bits, so you get 8 different addresses. Oh my god, holy shit. The entire 36-bit address space still begins initialized with value 0. The sum is 208. What is the sum of all values left in memory after it completes? Let's take a look at our input again and see how many X's. Oh, there's so many X's in these. What's this? It's like... Just this one random one. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. So that's going to give us 256 addresses. What about this one? So there's 8 there, 256. What about this guy? 7. Okay. It's still going to give us a lot of... I mean, this is going to fill up memory probably. But it's going to be... Here, let's see. 1... 4, only 4 there. So let's say there's a maximum of 8 each time. So how many times do we see mask? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So let's say there's about 40, so it's going to be 256 times 40. It's going to be about that many array elements that we have to worry about. Okay, it's, you know what, it's probably fine. Okay, so let's rescue some of our work from earlier. We may not use all of it, but I think we'll probably use some of it. These assertions are no longer true. And also the way we apply these rules has changed a bit. So it's our process line is going to change a bit. In fact, yeah, okay. I guess the way that we run apply mask is going to change. That's really because we're taking a mask, and the mask can actually modify several memory addresses. So this is no longer going to be true. So we've got here is that it first applies the bit mask. After applying the mask, 4 bits are overwritten, 3 of which are different, 2 of which are floating. Floating bits take on every possible combination of values with 2 floating bits. Okay. The program is about to write a memory address of 26 with a different bit mask. Okay. So I guess what we want to do is we want to. Okay, so we're going to assert that mem42 actually updates 4 things. Okay. So apply mask, let's change this. Apply mask is actually going to give us a new array back that we can then, or maybe it can modify the array in place. Maybe what we'll do is we'll apply mask and mem will be will be an argument. And the input is, mem42 equals 100. But it's actually going to be, so mem42 may not get written, so it's going to corrupt the memory address itself. So it's, okay, so apply mask is going to give us mem address and then a mask and then the value that we're putting in. And we are going to modify this in place, which I hate doing, but especially in JavaScript, because you can't have a bang like you can in Ruby to say like, hey, this is a destructive operation. So apply mask is going to take these new arguments. So mem equals an array and the address equals, this is an int. And then I guess int here is actually just, this int here is just the value. Okay. Cool. So with our input, we're going to get these, and then we're going to get these, and then the sum of that is going to be 208. So that's actually what we're going to assert. Apply mask. So processing line. So we just update the mask. That's fine. Now applying the mask, this is going to change as well. So first we split the number, the value into the bits, and that's fine because we're going to be doing that. Now what were the rules they said? If the bit mask is 0, okay, so we need to treat these differently. So right here we were just saying, hey, when it's not X, we're just going to overwrite it. So that's no longer a thing. And okay, so for every character in the bit mask and the index, what we're going to do is we're going to switch on the char. And when the char is, well, let's just go here. When the char is 0, memory address bit is unchanged. When it's 1, the address bit is overwritten with 1. Oh wait, this is going to be a problem. So because we actually have to so we're gonna have to do some reality branching here, or some we're gonna have to basically write these things twice. So we're gonna have to come up with every permutation where there's an X. So what I was going for is I was just going to have a different rule for each one of these. So if the bit mask bit is X, the corresponding memory address bit is floating. So I guess maybe what we can do is we can say we can split addresses. So we can say, hey, for every character where there is an X, so let's do that. Let's permute. Let's call permute to get every permutation of mask. So masks equals permute mask. And then we're gonna have to write permute equals, and it takes a mask. And basically what we're gonna do is we're gonna figure out what masks we should be applying. And then we can apply them all. Okay, so we're gonna do something similar here. So for char idx in mask split. Okay, so we're gonna turn it into an array. And we're going to have to find the number of X's. And we're going to have to substitute the number of X's, or the X's, with, excuse me, with like a number of times. I wonder if there's like an easy way to do this. We could apply it recursively. Okay, so for let's say mask array equals mask split. And so this mask array is going to give us an array that like looks like, oops, 0, 1, X, 0, 0, X. So it's going to give us something like this. And what we're going to want to do is we're going to want to say, hey, the first X we see, I want you to replace this with a 0 and then call permute against that. And then I'm going to replace it with a 1 and then call permute with that. So I guess the first thing we need to do is, okay, so maybe we don't need to split this into an array just yet. What we'll do is we will say if X is, okay, so maybe we don't need to split this into an array. We will say if X dot test mask. So if there's an X, what I want you to do is I want you to call so we're going to do two things. We're going to basically call permute with mask replace X with 0 mask replace X with 1, and this should replace the first instance. And this is going to give us an array of results back. So we're going to want to union the arrays, I guess. JavaScript array join. We want to. Can we just do that? Or concat? Is it concat? Concat? Oh, not join. It's concat. All right, concat. Let's take a look at concat. B, C, D, E, F. Yeah. So array concat array2. Okay. So we'll do that. We'll say ret dot concat the result of that, permute mask replace. Okay. And then we will return ret. Okay. So let's test this permute method and see what we get. So let's log permute. We'll put in a mask of 1x 0x. So, or let's just start with that and see what we get back. When 1, oh, it doesn't like, oh yeah. So let's just back out of this stuff and apply mask. Yeah, we don't care about this yet. So this is giving us an empty array. This is not what we want. So if x test mask, okay, so we're gonna log yes. So it logged yes once, and then let's see what log that is, and we'll log that. So that's exactly what we want it to be doing, but then what is permute? Oh, you know what? Permute. So we're never adding this. We're never adding this to the output if it's not. So if, so else, we want to just reply with mask. Okay. And we're gonna ret concat ask. Nope. So permute mask replace 0, 1. Okay. And so if x test mask no, then ret concat mask, and we're overriding return each time, but this is just because we're collecting our return values and then we're concatenating from what comes back. Okay. So this, oh, maybe it's not an array of mask that we want back. Maybe it's just the mask that we want to put in. Or it would be push mask. Log, no, there's no x's. And why are we not? So this should be giving us an array. We should be adding this to our existing array. So log ret. Whoops. This is still giving us. Let's log permute. Yeah. Maybe array concat is not giving us. Maybe we have to assign it. Yeah, that's what it is. We have to assign it. Okay. Yeah, it's weird that like push you don't assign, but concat you do assign. Okay. Let's get rid of some of these logs. Log. It's log. It's big, it's heavy, it's wood. So here's a thing that we can do now. So this is one of those things where we're doing like, oh, if that, then this. But what we're going to actually do is we're going to do the opposite. We're going to return mask early. We're going to return this mask here, and then, oops, and then what we're going to do is if that doesn't return, then we're going to concat these. And in fact, we don't need to initialize this. What we can do is we can actually just we could flatten this array as the result. And I mean, this is basically the same as saying ret equals that, return ret, and then ret equals ret dot concat. So, you know what, like rather than import flatten and use it, we can just do that. Okay, cool. So this is that, and then if we add another x to the equation, we should get 4 of them. And if so, you know what, like rather than import flatten and use it, we can just do that. Okay, cool. So this is, we add a third x, we should get 8 of them, and if we add a fourth x, we should get 16 of them. Okay, cool. So I feel good about permute. Permute is working how I expect it to work for now. So now we're going to get a list of possible masks from our mask, and what we're going to do is we're going to say for new mask in masks, or in permute masks, for possible mask, I don't know, no, new mask is fine. Full mask, I don't know, no, new mask is fine. What we're going to do is we're going to apply these rules. So for char index in mask, new mask, and then we can apply the rules, which is, what are the rules? If it's a 1, do nothing. No, overwrite ones. Okay, and if the bit is 0, it's unchanged, and if the bit is x, which it will never be, so we really just want to overwrite the ones at this point. So split when mask, or when char is 1. And what are we doing here? We're going to do bits index equals so this is going to be new bits equals bits. This is going to be a string. Can we new string? Can we just do this, new string bits? We'll say new bits, and then we can what are we going to do? This is the value that we're actually doing, isn't it? Hold on. So the mask is that. Doesn't modify the values, it's modifying the address. So the bits is not the value, the bits is this is the address equals, bits equals address, string pad start split. So this is the new bits, this is actually represents the address. And then what we're going to do is we're going to say address, and then we're going to want to parse float that guy. Where are we doing it here? We're doing it somewhere here. Parse in bits join. Okay. So this is going to be our address. Except we'll be overriding address here. So this will be new address Ugh. And then parseInt new bits. And then we're going to modify mem at new address equals value. Okay. So that applies mask. And then some array. So we're going to call apply mask. So this is a destructive operation, which is just modifying this in line. Okay, cool. So what are we asserting? We're going to assert that that's true. Is that true? No, it's not. Why is that? Adra is not defined. Adra is not defined. Where, on what line? Line 77. So, oh, there you go. Now new bits join is not a function. So new bits equals new, oh, because this is an array. Oh, okay, great. Bits. Oops. Assertion false equals true. Okay, so we just got a different number. So let's log what we did get just to see where we are. So 406 and we want 208. So I guess what we can do is we can start to deconstruct this and take a look at what the addresses that it's logging are. So let's look at that. Let's do that in apply mask and permute mask. So let's log new mask and see what it's giving us. So what did it say we should have? 11010 11010. So 011, yeah, 111010. I don't know where that one is. I don't see it. Okay. So the problem is we're asserting there. Okay. 10010. Where is it getting that from? 10010. So that's the mask that it's sending in for 42. So let's also, okay, so we're logging that, and let's log the value that we're getting in. Log the value, or I guess adra val. Okay, so 42100. So these are the bit masks that it is giving us. 010010. And what does it say we should have? 011. So this is giving us a different answer, I think. So that's the address, decimal 42. So maybe we're not applying decimal 42 to the address. Is that what it is? So address. So what we're doing is we're overwriting it when it's a 1, and we're leaving it alone otherwise, because we are expecting the permutations of mask to take care of that for us. Let's log mask. Okay, so this is our mask. So we get 0101 and 0011. So that's correct, and then 1001 for that. That looks correct to me. So why is that different from what they have over here? So 011. So they have a 1101, and we just have a 1001. So that's fucked up to me. Why is that? So decimal 42. Oh, do we have to pass? Program goes to write to memory just 40. It first applies the bit mask. So it first applies the bit mask. So we are applying the bit mask to the value. Doesn't modify the values being written at all. Okay. But clearly it is doing that. Wait, decimal 42, that's the address. So we have to apply the bit mask to the address. Okay, so when this program goes to write the memory to address 42, first it applies the bit mask. And after applying the bit mask, 4 bits are overwritten. So this is decimal 42. So are we the address to string pad start split? So let's log bits dot join nothing. Okay, so 42. Oh, come on. What is going on? Bits. Oh, is address. Oh, you know, it's because we're not changing the address to binary. That's why. No, but that's what this does. What? 42. Oh, because maybe, because address isn't parse float address, maybe. Okay, so let's do parse float address. Okay, yeah, okay, so we weren't parsing it as an address. Okay, so we can get rid of these logs now. And no, still not an assertion, so let's see what else we did. So it's giving us 202 instead of 208. All right, so let's put these logs back. Okay, so here we go. So bits join nothing. Oops. Okay, so and then the mask, then we're gonna log just a dot so we know where the separation is. Okay, so this is the address and the value. Okay, then this is 42, so this is the mask. So we're not applying the mask to the address first. And that was our old apply mask, which is let's like apply mask simple mask, and then we're going to take the mask and the int, and then what do we want to do with this mask now? Okay, it goes to write memory, first applies the bit mask, and after applying the bit mask, 4 bits are overwritten. So basically what it wants to do is it wants to take the decimal number, and if there's a 1 here and a 0 there, then it wants to update the 0 to here. So, okay. Or if the mask is not a 0, then it wants to overwrite whatever's here. I guess we can do that. Okay, so for God, what were we doing here? How are we applying this mask before? We're doing that. Okay, so we're going to apply the mask first. And we're doing this to bits. Okay, so or no, we're applying bits to mask. What are we doing? Okay, so we've got this address and we want to update the mask with the address, so we get the resulting mask. So we want to go through address, which is bits, and we want to alter the mask so that the resulting mask, if the resulting mask has a 0 and address has a 1, then it gets the 1. So it's really saying, oh, apply the mask to address. And then after applying the mask, 4 bits are overwritten. Three of which are different, 2 of which are floating. So I guess we're not really modifying the well, we are modifying the mask kind of, but we're also not. I don't know. Let's try it this way. Let's try modifying the mask. So we're gonna have to split out mask, because right now mask is just a string. Equals char for when char, and we want to look for just the ones where char is 1, and this is going to be in bits. Yeah, so mask bits equals mask dot split on nothing, and then mask bits, and then mask equals mask bits join nothing. Okay, sure. And that gives us 202, and that's still not what we're looking for, so that's not correct then. And then let's log mask here. Mask is mask. So that gives us a new mask of 11101x. So this is always setting it to 1, but we don't want to do that. We want to set it to 1 when char is 1 and new bits index. The only case is when it's 0, I think. So this would give us no and new bits. Oh, whoops! This doesn't go here. This goes here, and it's mask bits. This is very confusing, and this gives us 202, which is still not the right answer. But is this giving us the right mask? So x1101x and x1101x. It is giving us the right mask, so that's nice. And then that gives us 011010, 11010, 11111, 11100, 11111. So this is giving us the right output here. Okay, and then we've got 8 memory addresses. So starting there, yeah, 1, 10, 11, 11. So that's correct. So this results in an address with 3 floating bits, causing writes to 8 memory addresses. Okay, the entire 36-bit address space still begins initialize the value at 0 at every address, and you still need the sum of all values left in memory at the end of the input. In this example, the sum is 208. Is that true? Is the sum 208? I mean, I don't see why not. This is giving the correct masks, and I guess what we need to do is new address equals parse int new bits join 2. So let's log these. New mask hasn't changed, so let's log new mask and then the result, and that can give us an idea. So 58, 59, 58, 59. So that's decimal 26. That's not correct. Parse new bits. Huh. Unless this is wrong. So this would be 1, 2 plus 4 plus 8. So 10 plus 16 is 26. So this is 26. So parse in. So this is the mask. Oh, and the mask and the value together, right? So these memory addresses are written. Maybe that's what we're doing. New mask when char parse int new bits. So new bits and then new address. So the mem of this new address is val. But the new address, this should be address 26. So let's take a look at, so this is new mask, new bits. So 111010. So what am I doing wrong here? New bits. So we apply the mask first. And then for new mask and permute mask, new bits equals bits. So we create a copy of bits, which is the existing address. And then we apply the mask to it. And so we want to make sure that this mask gets applied to, I guess we should log the value. Log. Let's log that. Join. Okay. So we're applying this and this mask together, which should give us 11010, 11010, which it does. And yeah, but what about here? So 10. Oh, you know what it is? It's because it's not applying it. So the mask, theoretically, the X would override the 1. So maybe what we need to do is we need to apply these. Oh man, this is annoying. So this permute thing, so this is giving us back zeros, which we normally wouldn't apply, but we want to apply the zeros. Let's read the question some more. Okay, after applying the mask, 4 bits are overwritten. So it's going to be, we need to apply the mask before we permute it. So we apply the mask first, and then we permute the mask. Oh, maybe we don't need to be permuting the mask at all in here. So maybe what we need to do is we need to apply it first, and then we permute it. So we apply it. Okay, so let's apply the mask, and then we'll make permutations with the x's. When char isn't 0. So let's, whoops. So this is permuting the mask, which we don't want to do actually. We want to, what we want to do is we want to say bits. We want to basically do this, bits idx equals char. Okay, for char index in mask. Okay, so we're going to create a new address bit array. And then what we're going to do is we are going to basically, for the address in permute bits, so we're going to permute them here, and we're going to write the memory address address. Okay, so let's try that. That's actually a lot simpler. So we're permuting, so we're applying the mask, and then we're doing the permutation with the x's intact. So that's crashing at something. Reduce of empty array with no initial value. Okay. So let's see what we got here. What's bits, log bits join, and then log permute bits join. Okay. So, and let's get rid of these for a second. Log, let's just get rid of these logs for a second. Okay. So, okay, so this is going to be let's log bits here as well, and then we'll whoops log nothing. We'll put an empty thing in here. Okay, so this is the unpermuted bits. This is the, or sorry, the unmasked bits. This is the masked bits. Then these are the things that we are looking. Okay, so that's permute bits join that, and let's map these through to get the decimal values, just to check it out. Parse int string 2 26, 27, 58, 59, which is what we want. And then 16, 17, 18, 19, 24, 25, 26, 27. So, okay, so now we're getting there. All right, so this is giving us the correct thing. And then some array, reduce of empty array with no initial value. Oh, because we're not returning mem at the end. Is that all it is? Okay, that's probably all it is. Let's find out. So no, it's still reduce of empty array. Oh, we don't need to return mem actually. So it's actually, so okay, we want mask and mem back is what we want for process line, and process line returns mask and mem. This applies mask mem. Okay, so this is I guess what we can do is we can return new mem from here, which is what we were doing here. And then up here, what we can do is we can say mem equals that. And that's still not reduce. Okay, where's this reduce failing? Add array reduce, null, line 104, line 83. So line 83 is calling some array of memory. And process line should be returning mask and mem. And then line 104 is some array. Line 114 is where we're just logging process input. Okay, so somewhere here it's saying, okay, let's log mem.length. Let's just log mem.length and see mem.length is 0. So apply mask should be returning mem, which it gets in here, and it's not. So permute bits. Oops. Let's log mem.length here. So mem.length is is 0. So mem should be an array, and it is. And then when we add in permute bits, so it doesn't seem to be doing the thing. So let's log. Oh, so it's doing a bunch of things. So let's log add val. Oh, of course it's not. It's what we want to do is we want to mem add parse int the address as base 2. Yeah, okay, cool. Now we can do that. In fact, I don't think we need to return mem anymore, and I don't think we need to mem equals anymore. I think because it'll just be passed by referenced. Yeah, okay. Cool. And process line, I mean, this is getting a new mask back every time. It doesn't need to pass the memory array back, but it is, and that's okay. Okay, so 208, that's what we wanted to assert here. Let's try this and see if it gives us an answer. Well, shit, that's taking a while. I mean, it shouldn't be taking that long. What we have permute bits for line and text split. So permute bits. So permute bits. This will double the number of runs every time it sees an X. But I mean, that should be up to 256 calls per line. Okay, let's cancel that. Let's see which line we're processing. So process line, process input for line IDX. Oops. Log IDX. Let's say processing sing line. So it gets to 548. Line 548. How many lines are there? 549. So let's spit out the line. What line is it getting stuck on? Log line. So it's getting stuck on this guy. Oops. Literally the last line. And then process line, so process input. So for line, and then return some array log bool. Yeah. Log process input. Is it the sum array that's taking forever? Log what? Yeah, result equals. Okay. Yeah, so because I was here in sum array. Holy shit. Okay. So I guess it's just a huge array and it's having trouble summing it. So it's reducing the array. What about array values? Maybe we can sum array array. Yeah, okay, so this is just gonna take forever. So let's JavaScript sparse array. Okay, sparse array is one where the elements do not have continuous. Normally the length of property of an array. Okay, so sparse arrays don't fear them. Okay, well, I'm fearing them now. Yeah, where are we gonna look? Our JavaScript arrays sparse 2018 and an adventure in sparse arrays. Okay, I'm up for an adventure. There's both undefined, tripping over maps, walking in sparse line. There's two ways to guarantee iterating over elements that don't exist. Classic loop, which is sort of what we're doing. We're doing a map. There's new ES6 array methods, values and keys, both of which include sparse elements. Sometimes sparse is okay. Array of length 1 million. Okay, in summary, a trailing comma in array is simply ignored. So filter will return a new array excluding the holes. Entries. Array entries. Array spread will transform holes into undefined, which will also increase memory and affect performance. So entries includes undefined. Map including the holes. So map will include the holes. Okay, iterating methods such as map for each every won't call your callback for the whole. Okay, so let's change some array from array reduce. We'll just say for val in array. Okay, so num equals 0, and then num plus equals to val, and then we'll return num. So let's try that. So some array, and this should return assertion error. Yeah, why is that? Log, not a number. Is it because, oh, are we putting not a number? So some array for num plus equals parse float val, still giving us not a number. When val, okay, when val, and it's still taken forever. Still taking forever. So this isn't actually helping things at all. Whoops, come back. Array isn't defined. There, array. So not actually helping. So why? So I mean, some of these numbers, these memory addresses are very big. Oh, and when they do these, oh man, when they put these X's at the beginning, like these memory address masks are going to be friggin' huge. hot damn. Okay, well, let's stop this and think about it. So the problem is we've got these sparse arrays with very, very large addresses. And it wasn't a problem when the addresses were like 50,000, but it becomes an extreme problem when it's whatever the fuck these numbers are. So let's look up JavaScript arrays with large. You know, they don't have to be arrays. You know, why does this have to be an array? This can be an object. Let's do that instead. Let's make objects. That's probably easier. An array is basically just an object with a numeric thing, and we're not ever calling the whatchamacallit, like length or anything. So okay, so memory is going to turn into an object. That's what I've decided. So apply mask mem, okay, and then so what do we got here? Mem, it's gonna be an object. Okay, so some mem dot values. So we're gonna call object dot values mem. So that's gonna reuse some array. So return, that's fine. Apply mask mem equals that. And it's fine. It's going to be a number, okay, and find mem. So that's fine because that's object notation instead of array notation. And all right, so mem's an object. We're not doing mem like push anywhere. Nope. Okay, let's try it. There we go. Got a very big number. And let's see if that's the right answer. Survey says that's the right answer. Hooray! Okay. So what did we do there to make that work? So really, I mean, an array is like kind of an object where you can call like array 0 equals, you know, 1, 2, 3. Array 1 equals, you know, 4, 5, 6. And then at the end of the day, what you basically get is an array with an entry at 0 of 1, 2, 3, and an entry at 1 of 4, 5, 6. Now arrays are a little bit special because you can say like a dot length, and that would be like 2. It's a dot length. However, if you went like a dot 2 equals this, then you'd have an object like this, and 3 would be array dot length because it's really just sort of like what's the biggest thing in your array. Arrays have some other properties too, but I mean for the most part they're sort of indistinguishable from objects in that you could have like object, right? And you can say object dot 0 equals 1, 2, 3, and object dot 2 equals 4, 5, 6, and object length isn't even a fucking thing, but you can get the values of an object and call that, which is what we were doing. We were saying object dot values of O, and we can call length on that, and that will return these back as an array. So that's basically what we did, and that's how we made it work, because JavaScript having to think about an array that's so big, and then you're like, oh, what's the sum of all the things? It's like, let me start at 0, and then go to 1, and then go to 2, and then go to 3, and all the way up to whatever quintillion or trintillion. It's going to take a very long time. But with an object, it doesn't store the data that way, so it doesn't iterate over the values that way. And we didn't even care about the addresses by the time we were done. All we cared about were the values that they held, and there was like a limited number of those. Anyway, so that's why we did that. Let's see what this looks like. Yeah, it looks all right. Okay, so let's take a quick look at the code here and see if there's anything we can learn or take away from it. So process line, basically, if it matches the mask pattern, do the mask thing, update the mask. If the line matches the memory pattern, what we're doing here is we're applying the mask directly, and this is passing in the memory object, and the memory object is being passed by reference, so we can modify it. And then at the end of the day, we're just returning mask in memory. So process input, this is basically sort of the loop that calls process line. So I guess we could put that there. In fact, process line, I mean, could be broken into, you know, process mask or update mask and whatever, and we could do this pattern matching in here, but it's okay. So basically, this just takes the text in. This actually initializes the mask in the memory as well. It doesn't need to, but I mean, we could take that out and it would still produce the answer. But if I'm tracking them and using them, then I'll probably want to initialize them. At this point, we don't even have to initialize them here. I don't think, or maybe we do. Line is not defined. Oh yeah, it's mask and mem, it's these two. So we actually don't need to initialize the values here, but because we're passing them in, I like to have the initialization values as a hint as to what we're expecting. It's sort of like a poor man's type safety. Okay, so if it's a mask, we do the mask. Okay, that's fine. We did that. We're processing these lines, and we're always returning the new state of mask and memory for each one of these lines. And then at the end, we're just summing the values of the memory object, which is fine. Permute. So this is something that, we use in apply mask. So it's almost like a helper to apply mask. So apply mask, what are we doing? We're taking in the memory address. So this memory address is a number. We're parsing it as a float. Then we're turning it into a binary string, and then we're padding it with zeros, and then we're splitting it into an array. So this is going to give us a bit array, effectively. And then we need to apply the mask. So we're going to overwrite this bit array with the mask whenever it's not a 0. Because remember, that was our rule. Our rule here was, yeah, if the bit mask is 0, it's unchanged. So basically, we can just skip the zeros. We don't do anything with the zeros. And then these rules will get applied later on. If it's a 1, we want to overwrite it. And if it's an X, we want to both write it and overwrite it. So we want to split on those. And that's where permute comes in. So really, this address bits thing at the end of the day is going to be a string of zeros, ones, and X's where we've already applied the ones. And then what we need to do is we need to get a copy of that with a 1 and a 0 for each one, which is where permute comes in. So permute just says, hey, if your mask doesn't have an X in it, give me the mask back as an array of a single mask. And if it does have an X in it, then we go further and we say, okay, so let's collect, we'll say, give me the mask with the first X replaced as a 0, but then run it through permute so we can basically recursively get those. And what that spits out is every possible combination, as we saw earlier. And it does that once for O and once for 1. And so that just gives us a list of possible addresses that we're going to write to. And then we have to write to the address where we go back to the integer value for that address. I guess we don't even need to do this anymore. We can actually probably just do that like that, and it will still give us the same answer. This was just because we were using an array. But because we're not using an array, it's an object, we can actually just have that be the address string now, and that cleans that up a bit, which is nice. Cool. So let's leave a note here where we, what is it? apply the mask to the address, preserving the X characters. And then what we want to do is write every possible address permutation. Cool. And then apply mask doesn't have to return anything because this is a destructive thing. This will update mem with value, with val for every address permutation. Okay. And I'd like to call these out when I'm doing a destructive operation, especially in JavaScript. Okay, so that applies the mask, even though it's called apply mask. Cool. And then some array just is a reducer. Passes our assertion, gives us our answer, and we're happy about that. Cool. And this is part one. Got a bunch of assertions. Some array reduce memo value, that's fine. Mask pattern, mem pattern. So this, does it still work? Yeah, I guess so. Because this used to be OG, but now we're doing process line, process input. Right, okay, yeah. And what are the notes we left here? This is apply the maskle. So this is apply the mask to the value. And then this is parsed bits. This is return the int version of the new value. Okay. And this adds to memory out here, which means we don't have to worry about memory and apply mask. Cool, this still works. Neat. Yeah, I think that's good. I think we can leave it there for today. Cool. This has been another doozy of, I don't know, like 2 hours, maybe plus. But that was fun. Okay, cool. Look forward to doing this for day 15 tomorrow. So I'll see you guys tomorrow.